So my talk is about new approaches to linear propagation of acoustic fields. The propagation of acoustic fields from realistic sources involves significant effects of diffraction and medium attenuation. The Rayleigh-Sommerfeld diffraction formula provides an exact analytical solution for the effect of diffraction on any linear field. For most of the fields and propagations of interest, though the analytical solution to this formula is unavailable and the direct numerical evaluation is almost impossible. Also, this formula is an expression of Huygens principle, which characterizes diffractive propagation as that of the linear sum of fields constituent point sources. As such, the diffractive propagation, characterized by Rayleigh-Sommerfeld equation, may be viewed as a convolution of the fields, or usually a source, which is being used with an appropriate point spread function. As it well known, the convolution of functions in one domain can be represented as a multiplication of the Fourier transform of the function, and thus many have used the efficient fast Fourier transform approach to convolutions to calculate diffractive propagation. One of the first works that addressed the potential of such transform as Fourier transforms for the computation of diffractive fields propagation was Radcliffe's. In this work, Radcliffe used the fact that a two-dimensional Fourier transform of a harmonic field in a plane is equivalent to a decomposition of such fields into a sum of harmonic plane waves traveling over a spectrum of angles. This equivalent sum of plane waves is referred to as the angular spectrum of the field, and it allows the diffractive propagation of any harmonic field between two arbitrarily distant parallel planes to be reduced in complexity to that of plane waves propagating between the same planes. The angular spectrum concept is the transform domain equivalent of Huygens principles. Radcliffe covered a wide range of cases to illustrate the application of the angular spectrum decomposition to diffraction theory, although the specific application of interest was radio waves in ionosphere. Optics textbooks such as Goodman's or Gaskell's also discuss such methodology. But in acoustic, the angular spectrum methodology has been utilized by a number of investigators in a variety of applications. Different scientists and their works used to investigate the possibility of sub-wavelength resolution acoustic holography. And this allowed them to apply these methods, the methods of Fourier transformation to approach different solutions of such fields. Also reported that investigation, except those which were also explored, it was important topic of windowing in finite length discrete operations. The windows investigated included those applied in spatial domain to the point spread function and those applied in spatial frequency domain to the analytical transform of the point spread function. Most recently, there was a work about the angular spectrum methods to the problem of propagation of acoustic fields for the purposes of transducer characterization. So the main idea of this was to apply different plane waves to and summarize all of them to calculate the fields of different maybe strange sources.